What's going on there? Okay, so it's really a pleasure to be around here. I haven't been in Japan for 10 years, so I was very glad to be invited here. So I hope people will like this talk, even though I almost did not manage to make it in time due to like strikes and snowstorms I had to cross to reach through the through France to reach the airport. So yeah, this was a bit hard. So I'm very happy to be here again. Right, what's going on? Something does it work? Yes. So today I'm going to talk about something that, as Jacques mentioned, is something from my other hat, which is being a developer of a major proof of systems. Right. So before even talking to settle a little bit the situation. So here is a nice diagram of what a proof assistant looks like, just in case, like I know this is TPP, but I have to explain what a proof assistant is. So proof assistant is like this kind of nice black box here. I call like your favorite proof assistant 3000, right? And you are the circle here. You input things. A proof assistant outputs something. So here it is. And so what does the input look like? So typically you write a theorem, that's a formal statement, then you write a definition of your objects, then you write things like tactics, so that's so far so good. Then usually you insult your computer a lot so that it works, right? And at the end what you get is something that's like, yes, you did it right, or no, you failed, or some like very low level dump of horrendous data, like, you know, like lines and screens and screens and screens of errors, right? Yeah, so the title says that you're ecstatic about the use of proof assistance. That might depend. Right, so there is a very well-known proof assistant design called the LTF model, which looks like that. So if you open the black box that I gave you before, basically you've got this kind of separation between, on the left-hand side, the untrusted part, and on the right-hand side, what is called the kernel. And there's a thing here. This red line here is what I call the wall of trust, which means that basically you don't care about this part. So there's like potential very dark magic. So this is like you don't know what it's doing, miraculous things or evil. But it doesn't matter, because in the end, this is like the ground truth. That's the thing that is checking that your proofs are indeed correct. So outside of this, you don't care. And the important part is that the kernel here is small and hopefully understandable as a piece of code. So that's a very well-known design. There are two typical instances of this design in the world. So the first one is like the historical LTF, which is like still thriving in the whole proof assistant family. So basically, you can see that as some kind of API in your favorite well-typed programming language, like OCaml or something like that. And in general, you may not record the proofs. You only care about the interaction with the API. But there is another second kind where, when you do dependent type theory, you need to care about your proof terms, because like terms are important in they exist as elements in the types. So the kernel is, in that case, rather than just some kind of API, it's a type checker for your language. And the proofs are really literally well-typed terms. So you send a term to the kernel, and you get you type checks and say yes or no, and that's how it works. In this talk, I'm only concerned about dependent type theory, so you can forget about the first case. We'll be always in the second case. Right. So this is my favorite foundations for mathematics. It's CIC, which means the calculus of inductive constructions. So I'm not going to enter all the details yet, but basically some kind of very powerful dependent type theory. Depending on your point of view, it's either a programming language or a logical system. And typically, it's what we claim it to be, the idealized system behind Coq and lean proof assistance. Small parenthesis, Coq is about to change its name into Rock. So since I'm the next release manager of the name change version, this is the last time I can make a joke about roosters. Yes, so that's probably one of the last talk in the world. You should be happy. One of the last talk in the world where you actually hear about Coq. Right, and the full disclaimer is that I am a core Coq developer, so I will have a very strong bias towards Coq in this talk. And worse than that, Actually, I'm an extremely opinionated developer of the Coq proof assistant. But with a little bit of grain of salt, you can assume that whatever I'm going to say in this talk somehow can be applied to other similar systems. So, for instance, Coq and Lean are very close in terms of foundations. There are very technical differences I might highlight in the talk, but it's not very important. Coq does it right, obviously. And even with a little bit of exaggeration, some of what I'm going to say is also applying to Agda, which is similar type system, a bit different, and even though there is no kernel in Agda. So yeah, here's the big picture. What I'm going to talk about is mostly general and proof assistance. Yes, there's a joke I don't want to discuss. Okay, so to be on the same ground, I like in very short amount of time, I'm gonna tell you what CIC looks like. So is it a programming language or a logical foundation? So it's a purely rhetorical question. It's both. So depending on your point of view, you can use it as a programming language or a logical foundation. So if you start from the very beginning, like level 0 complexity, so you've got this nice function here, that's lambda xx, so the identity function, which has type A to A. If you see it as a programmer, then that's going to be the identity function. I mean, okay, I revealed my bias because I said that it was the identity function. So I'm a programmer, I'm sorry. And if you see it from the logical point of view, this is the canonical proof that A implies A as a very simple theorem, right? So we are all on the same ground, easy peasy. Level 1. So you can look at this fancy formula here. So it says something like M has type pi, M as a natural number, sigma p, either M equals 2p or M equals 2p plus 1. So if you see it as a programmer, that's basically the implementation of division by 2. You see, if you give me a natural number, and I produce a number such that if I multiply it by 2 up to 1, it's going to be the same thing. And if you see it as a logician, basically this is something about primal division by 2 or something like the fact that you can divide by 2. Okay, you've got this nice fancy, so that's my favorite type in CIC. So this is the thing that separates the baby type theories from the big type theories. So this is the case when you can. So this is M is a function here that takes a nice Boolean. So you know Booleans are nice, are only 2 Booleans, true or false. And depending on the value of the Booleans, returns 2 different types. Either it's a natural number if the Boolean is true, or it's a function if the Boolean is false. So really, it starts to be weird, because in particular, that means that the runtime of the system is part of the type system. Yeah, you need to know what B is actually equal to decide what to do. So you can smell already that there is some complexity that's going to arise from this. This is the real part where dependent types matter. And then if you jump like to level 42 of the boss, like the final boss of the type theory, probably you can find new ones. You can just look at the specification of the concert certified compiler and try to scratch your head about what it means in terms of deep logical foundations or something. I don't know, but okay, you can write. Right. So this is why I claim that CIC really is like the utmost pinnacle of the Curry-Howard correspondence, the proof as program correspondence. It's really the best, the paradise of writing programs and proving them in one go. There is no, everything is the same nature. So it's a very nice system. Okay. So as I said before, we are interested in dependent type theories, and the kernel of dependent type theories are basically type checkers, right? So you take a term, and the type checker says, yes, it's well typed as this type, and otherwise it fails. Right. So there is a thing called reductionism. So this is a very famous example of, so this is a duck, this is not a rooster. But technically, that's a French. So like in the 18th century, some French guy decided that he would imitate nature by writing this kind of designing this kind of automaton. So that's a duck that if you give it food, then actually it produces a waste from the outside here. Okay, so normally this is a way to reduce like the phenomenon of digestion, you know, like you eat and you get this. So applying the same kind of reductionism, since CIC, the kernel of CIC is basically a type checker, that means that to understand CIC, it's enough to understand the kernel, right? Okay, there's a reason why I say famous last words. Oh, things are in it. There's a little bit little things. Well, some jokes in the title, so if you get them, it's better if you can get them. Okay, so I'm not going to interrupt, but so it should be enough in an ideal reductionist world to understand the kernel as a type checker. First problem, I lied. There is no such thing as CIC for various reasons. First, because there is not a single system, but a lot of systems that have been written in a lot of articles, spanning a lot of time. So it's like a distributed knowledge at its best or worst. And so as a consequence, in particular, somebody says that I can claim that something is CIC, somebody else can claim that something is CIC, and nobody's going to agree on what CIC means. So that's really kind of fishy. It's worse than that, because you could have systems that are extensions of one system or the other, but some systems are outright contradictory. People are saying, yeah, so this is part of CIC, this is part of CIC. There is also a lot of things that is not told. So there is people, for instance, nobody's ever gonna tell you things about bound variables like that. There's a lot of implicit things in the articles, and I think that the worst part is really this. There is a hell of a lot of knowledge that people, experts in the area, know about, that has literally never ever been written in. So I'm not even saying published, I'm saying written. So even in the code, there are things, invariants in the code that are known, but never made it explicit. So really we're entering kind of an uncharted territory where if you ask somebody, he's going to say, yes, it's very well known, and then you ask another expert and you say, what? So yeah, this is very bad situation. And if you look at the implementation, because you could say, okay, right, the paper, mathematics, that's all theoretical stuff. Let's go to the real ground, the real implementation. That's a concrete thing. If you look at the implementation, that should be a source of truth, right? There is code. Look at the code. What does the code do? And yeah, so normally the code does something with respect to some specification. And when you look at the core kernel, it takes a lot of liberties with respect to specification. You start wondering, but how does it even work? Right. But okay, that's one problem. But this is even worse, because now there is the same kind of problem as above, saying that if only we had a spec. We don't have a spec. But even if we look at the code in one point in time, actually the code changes. So if you look at the kernel version of some versions before, you will get a different answer. So you're like, nah, so what are we doing? What are we doing? There is no solution. Well, there is one. It's called a Mitacock project. So this is a shameless plug for some friends of mine. But this is not what we're gonna cover today. We're not gonna talk about the solutions. We're gonna talk about the problems that these people are trying to solve. Okay, so I think that this is somehow the motto of the people implementing type theory. So I'm going to read it out loud. So the non-existent type theory is based upon both logic and faith, right? Why? Because we have faith that it is implemented. We logically know that it does not exist because it is not well defined. So I think this is a very deep statement about type theory. So bear with me. Even though this is completely and outrageously inconsistent, doesn't matter, because we're at the level of faith, and we'll pretend in the remainder of this talk that whatever CIC means, there is some well-assigned meaning that I will be able to describe at any point in time, and switch back to some if you realize that I'm lying to you, I can always backtrack and say, no, but that was not what I meant actually. So let's assume that there is such a thing that we call CIC, the idealized theory behind the clock and mean prefix systems. So this is a very medieval thing. This kind of thinking is a scholastic, right? So it doesn't matter, how many angels can you fit in on a needle pin? Right, so that was the original reductionistic claim. Okay, so right, there is no such thing as CIC, but we assume that there is one. So we can still reiterate our claim, reductionistic claim, sorry, saying that clearly it's enough to understand CIC to understand the kernel. Right, good, because there is such a thing as CIC. That's an act of faith. Okay, unfortunately for us, even that is not true. And the reason for that is what I call personally the notion of asperity of reality. So I'm going to try to explain that with a weird metaphor. So here we've got on the left-hand side a nice map. So, you know, you see there are borders and like nicely colored areas and names and whatnot. And then on the right-hand side here, you've got some kind of already approximation of reality. And if you like stare enough, you can realize that there is much more information in there than there is information in here. And this is like a typical map versus territory situation. And if you really look into the details, there are things that matter. So there is the motto is like a specification is not an implementation. So this statement, the asperity nature, comes from I think it was a Hacker News post or something about somebody trying to build stairs. Like, you know, it's easy. A stair is like you have steps, and you get the thing, and you get the planks, and you get the stair. But if you look into what happens for real, like there are a lot of tiny details that get in the way because you have to cut things in a complex ways when you reach the extremities and whatnot that nobody has ever told you about when you actually try to, out of the blue, try to create a stair. And the same thing happens in a much worse way with software systems, because software is very complex. So there are in many ways, your implementation can refine the specification in ways you have never thought about. Okay, nonetheless, so I'm going to come back to that after, but nonetheless, I would care about the good, I have a few good properties about the non-existent system I care about. So property one is like, oh, I'm a logician. I want my logical system to be consistent. So there is no proof of falsity. I assume that everybody agrees with that. But at the same time, they are starting to bargain, saying, oh, yes, but I want this and that and that and that in the logic. So it has started to have like a complex system you have no clue about. The programmer says, oh, yes, I care that my programs actually evaluate to things that have a nice shape. So for instance, natural number evaluates to a numeral. And then they say, oh, yes, but I also want to have like all these fancy features in my programming language, like pointer equality, exception, blah, 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 right? And then there is the third person, like the maintainer. So that's a triangle, you know, like the maintainer cares about things like decidability or type checking, for instance, but that's one of the things. But they also, as implementers, they like to extend their kernel saying, but I'm also going to add all these fancy features to my kernel because it makes things easier. And the worst part, so this is like a triangle equilibrium. There are three persons implied in this triangle. So if you want to have more an extension of the logic, you must preserve computation. Not like there are three edges to the triangle. So you have to be careful when you add axioms, and some things do not even compute properly if you cannot axiomatize them. If you add things to your computational constants, then you care about preserving the consistency of the theory for the logician. So there are a lot of constraints I'm going to come back about after that. And in particular, a lot of things people do in PLT just do not work. Like in PLT, people, most of the time they cheat because they have non-termination. So when things go wrong, they just say, I don't care, I'm going to produce some crap. In type theory, you have to do something well-defined. There is no way you have a UB in CIC. So you can't cheat. And from the maintainer's point of view, you still want to keep the implementation okay. So you want to have like a spec you can kind of trust with a smallish implementation. Something nobody tells you about, like what efficient algorithmics. Like there is no purpose if you have a kernel that takes the age of the universe to type check a term. So it's something nobody tells you about. And the dreaded backwards compatibility, because like if you look for too long at the kernel, you're going to break code in the wild, and people are not happy when you break the code. So you have to take that in. And the worst part actually is that, at least in my case, these three people, so that remember there is a triangle, like a logician, a programmer, and a maintainer, are the same individual. Like depending on the time of the day, I'm one of these three people. So this is kind of a multiple personality situation. Okay, so this leads me, the overall constatation of this situation leads me to the following. This is like one of the most, the nicest traditional food, French food. So it's called an andouillette. So it's some kind of, these are tribes. The tribes are set, right? And it's famous for being the source of an aphorism by a former head of the French state from the 1930s, Edouard, I think is the first name, Herriot, right? So head of the state. And he said the following. So I didn't write it in English because of the rudeness, but I tried a Japanese translation here. So I'm going to read it in English. So a kernel is like an andouillette, so this kind of tribe sausage. It must smell a little bit like shit, open quote, end quote, but not too much. And that's precisely that I'm going to call that the andouillette principle, because like a kernel is precisely the interface between like mathematical world and reality. So there must be, like, to be enjoyable, there must be a little bit of shit smell, but not too much, because otherwise you're in trouble. So now that I've properly set the situation, I'm going to look into three components of the kernel: the conversion, universes, and God, while keeping the andouillette principle. So I'm going to look for some kind of shitty smell and ensure it's not too much. But now you can brace, like start, brace off and be like, we're going to enter the kernel. Okay, first thing, the conversion. So this is the most important rule of CIC. If you were like, I know people have been eating, so if you were like after lunchtime dozing off, you can wake up. So if there is one rule you should know about CIC, yes, I'm looking at the audience, like that's the one rule you should care about. It is called conversion. So conversion is a rule that says that if you have a term M of type A, right, and I know that A is convertible to B, whatever that means, then actually M has type B. Okay, so it means that I can replace equivalent types everywhere in the derivation at will. That's the thing that makes the following work. If I have REFL, the proof that x equals x for all x, the reflexivity proof. If I apply it to 2, then magically it becomes a proof of 1 + 1 = 2 by conversion. And basically that means that really in dependent type theories, computation is hardwired in the logic. Like there is the whole runtime of the programming language that flows into the type system. And this is not something you really see in normal languages. Like if you take your favorite functional programming, like a camel, like you don't get this kind of a horrible, like the runtime, and there is a phase separation. The runtime and the compile time things are not the same. And here there is no way to escape from this once you realize that you're in this situation. This is really something very specific to our dependent type theories. So I claimed, yes, A is convertible to B, but this is cheating. I didn't define what it means to be convertible. And I'm not going to enter the details, but basically you have the expected things, like, for instance, if you apply a function to an argument, then you can substitute. You have like the rules for reduction of pattern matching applied to the constructor, stuff like constant unfolding. So it's natural things in lambda calculus. The important point is that I said that as a maintainer, I want type checking to be decidable because I have an algorithm that decides it. So it has to be decidable by definition. So in particular, conversion must be decidable. And since the kernel is part of the type system, so the kernel must also implement conversion. Right. So you could say, oh yes, but that's a trick. We know how to do that. No problem. Easy. Well, if you look at the simple situation like Hall, there is not really conversion there. There is a very weak notion of conversion. And you can actually even do things called weak dependent type theories, where you replace the conversion rule by some kind of rewriting. It's a very hot topic, if I might say, with the double T. But if you look into it for real, then you realize that conversion can be like very positive and very negative at the same time. So since it's part of the kernel, it's magic. You don't have to care about it. Like it's a given. Like the kernel tells you, are these two things computable? So you don't have to rewrite things. So you are happy when the less work you have to provide, the happier you are, right? You don't want to write tactics if things can be automatic. That's the point of a proof assistant. Like otherwise, what would you like? There's a machine is there to help you. And in Holy, there is no way around. You have to write everything, but it's inefficient because you have to write the rewriting rules and explicit transitions. Here, it's magic. The kernel computes and says yes or no. So replace term by computation. And the other one, the weak dependent type theories, actually, this is only a theoretical thing. People who work in that situation, it's like you can look at what the computer outputs, but in reality, you cannot use these systems. They are designed as targets, like intermediate targets for compilation of systems. They are really a horrible assembly of your type theory that you really don't want to look into. So that's kind of the weak point of conversion, but there is a very strong point about the conversion. So since I claim that default CAC is a programming language, then you can actually use conversion in a very fancy way. This is called reflection, so you probably have heard about it, but I'm going to mention it briefly. Basically, the idea is to replace decidable fragment of your logic by computation. So you pick some logical theory, like rings or closed real field or stuff like that, where you have a decidable equation or decidable logic, and you represent your formulae of the logic in the proof assistant as a concrete AST data type. You write something that turns these formulae into actual propositions of your proof assistance. You write a function that tells you whether a formula is true or not, right? And you prove that indeed, when the function says true, then the property, the evaluation of the property is provable. And then, ta-da! It's very easy because now you had to prove something very complex, but you know that you can just call the magic conversion checker, who is saying, oh, yes, this function equals true, end of the story. So that's like a hammer to solve a lot of somehow logically trivial but computationally intensive problems. So you don't have to think a lot. You just call the tactic and boom, you get your result. So that's something that you cannot do in other proof assistants in such a very efficient way. And that's really a landmark of dependent type theory. This is something that is very, very useful in practice. Historically it was used to reduce the amount of memory used, and morally the way I can see it is like it's some kind of a logical JIT. The idea is really that you can teach the kernel to replace at runtime some kind of you can extend the logic by extending the logic yourself by you write the rules, and then the kernel learns about the JIT thing. Okay, so I'm going to and there is a similar idea that's called a small-scale reflection. It's not exactly the same thing, but it's very used by people in the math comp community, and it's used everywhere, and it relies fundamentally on computation as well. So the moral of the story is that computation matters. Very important. We do care a lot about computation in dependent time series. And you can see that very easily in the kernel, because we don't have one, not two, but we have 3 conversion algorithms in the kernel. So there is kind of the reference one. So there's like some kind of interpreter written in OCaml that's very clever at conversion of symbolic expressions. That is extremely sensitive because depending on the orders of evaluation and stuff like that, then you can get the blowups here and there. And then we have like 2 computationally efficient evaluation. So they are basically some kind of OCaml, morally some kind of OCaml runtime, and they are very efficient at computing true. They have one use. I give you a Boolean, you check that it is true. Okay, so nothing symbolic. It's very concrete, terms. And there is in this situation a trade-off, because like obviously if you use the one above for efficient computation, then it's slow, and if you use the ones below for symbolic computation, it's also slow. So there is like some kind of trade-off involved. We don't really know about the precise design space we could explore. I would like to mention Lean, for instance, that has another different kind of evaluator that does something different. So there is a lot of intrinsic things. I would like to attract your attention to the fact that this conversion problem is something very interesting from the point of view of what we can do. Okay, so that's one thing, but there are still more things to say about conversion. So, for instance, you can consider this nice. So I'm defining the subset of natural numbers here, such that they are even. Easy, right? And there is a little problem because in CIC, assume you have two such proofs that the natural number is even. Then, if the underlying natural number is convertible, there is no reason at all that the subset types are convertible here, because these things are pairs, right? Oops, sorry. These things are pairs. So this is proofs are programs. Remember, this is a Curry-Howard isomorphism. So this thing here is a program. So there is no reason a priori that two proofs are equal like that. So I would like to attract your attention that when you do that on paper, like literally nobody ever cared about that on paper. When you have like a proof, two different proofs that something is even, then like it's no good. Like you don't even care. Like there is not even a way to phrase it. But in dependent time theory, you cannot escape from that. So this is very annoying. We would like more conversion, and it's not just something theoretical. Like I'm not saying, I'm a type theoretician. I like to have like nice systems where I can reason easily, blah 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 blah. Actually, if you're really in practice, like it's a thing that happens like almost immediately. Like you take a first year student in doing comp assistant or something, and you write a nice script here. So and you get this kind of I'm not even going to even read it, sorry. But so, I'm just trying to rewrite an equality between natural numbers in a nice looking goal I didn't write here. And then you get like this screen long error message where you say, well, there is a variable they did not even name. There are like a lot of things, blah, blah, blah. I don't understand anything of what is written in that thing, right? And this is just like okay, you require a PhD in type theory to actually understand what that means. So my natural reaction to this kind of error message is the following. It's like, no, what the hell are we doing? Like this is nonsense. Like this is type theoretical nonsense. Why do I have to care? No way. I'm going back to hope. No way. Why are we using dependent type theory? This is really crap. And it's a very well-known problem. So we use it. It's a famous phasing. So I remember the time when I was younger, like we were given these kind of problems, and like you had to write the solution by hand and suffer for like a few hours trying to understand what was going on. It's so well known that SH reflects as a design pattern to work around this issue, but it's not inside the kernel, so it's like kind of hackish, if I might say. So this is a real problem that should be addressed, and it was actually solved recently by what is called strict proposition. So there is it has been a few years already where we introduced a new universe S-prop of strict propositions. So a strict proposition is really the nice notion of propositions. Like if you have two proofs of a strict proposition, then they are convertible by design, right? So it's really saying that the proofs are equal. And that was really, I think it was motivated by fundamental type theoretical, like the way, because it's hard to implement actually. You have to be careful about how you do it. So it was kind of intelligent, I would say. And yes, that was the important part here, that the kernel was extended in a non-trivial way. And it's extremely sensitive to subtle design choices. In particular, I would like to highlight the fact that Lin took the easy path, the dark side of the type theory, easy, faster, easier, but in the end, you suffer. Okay, but it seems to work. I'm not going to blame them. Really, the thing that's important is that this new kind of proposition is a game changer. And it solves a lot of problems that are well known in the time theoretical community, but it's not enough because there are many more limitations that are well known. So here is that's the next one in the series of hazing. So that one is I've got a function head that takes a vector of size 1 plus n, right? I want to apply it to a vector of size n plus 1. Easy peasy. You apply it, and then you get this kind of horrible errors because 1 plus n is not convertible to n plus 1. Well, that's life. And this is much harder to solve than just adding strict propositions. So there is a lot of work that is going on these days. These kind of problems were very fashionable in more than 20 years ago. Like there was a wealth of theoretical work trying to solve it. But but for some reason, I don't understand why, like there is some kind of curse. Like people do theoretical work and it never reaches actual implementation, or there are toy implementations, but it never reaches the concrete, like the major one. So people are developing examples in their side, and then nobody cares. So the hopeful point is that this question about conversion is making a comeback. So I've talked about the strict proposition thing that was implemented recently, but we now have a rewrite rule. So I'm not recommending that you use them for daily use, but it's a providing way to solve these kind of issues. There are also things called as extension types. So there is like a lot of current work in the foundation of type theory that is making a comeback about this extension of type theories. So the real question is like, will this cycle of will we forget about this again? Like, is every 20 years like the cycle of forgetting what people have done 20 years before? I don't know. I hope it will continue. Right. So here is the end for the conversion thing. I'm going to talk now about the second point about the kernel, which is like universes. Okay, so if you've been to a class-independent type theory, so one of the first things they tell you is that types are first-class citizens. So types, in particular, have a universe types, right? You usually write type. Require a lot of thinking, okay? And then you are asked the following question, because like type is a type. I mean, type is a term, so type as a type. I'm sorry that I'm using the same word type to mean type. So I'm trying to type with a type, right? Does it make sense? So what is the type of type? So there is a famous answer by the seminal paper by Martin Neff in 71, which is like, type is type. And then like literally a negative amount of time before, Gerard comes like it's like the cool head guy, like it just crashes through the wall and say, that's inconsistent. So for the little story, he knew before the publication of the article that it was inconsistent. Let Martin Neff publish the article and then said, that's inconsistent. Well, so he's like, so the standard solution, there is a very well-known solution to this problem, which is like to have like a hierarchy of universes. So you say, oh no, it's not just type, it's type with a natural number. So type 0 has type 1, which has type 2, blah, 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 up to the infinity. So like, I'm not saying anything deep here. It's a very well-known solution. So we are computer scientists. I mean, I am a computer scientist at least, and we love natural numbers. Like they have a lot of nice properties. Like they have a universal property of being the first infinite set or something. So like it's like natural numbers, like the paradise of natural numbers, simple, elegant, universal. And completely anti-modular. Why? Because like if you write type if you have a type theory that is designed this way, then you have to pick upfront a natural number for all your types. All right. Good. Now, assume that you have you pick a universe n, and you have an n as type n+1, and then you realize suddenly that you forgot one level, like you need one more level in between, right? So you need to create some m that is in between n and n+1. It's going to be hard. Natural numbers do not enjoy these kind of nice properties, so you're completely screwed up. Hints, like that's the hint of the trait. That's why you should increment your levels by increments of 100, so that you have enough room to introduce new universes. Okay, so that we did that in the basic time, like the basic programming language. Like you have a universe. Yes, yeah. People are old enough in this room to remember that. Yes. Okay, so this is completely crappy because obviously once you have to add 101 universes, then you're screwed. So okay, you gain a little bit of time, but not too much. So you shouldn't do that. Like don't do that at home, kids. Like, yes, natural numbers are not a great modular feature if you want to create this kind of names. Okay, so I spilled the beans already. Why not just introduce names? Like it's better, it's more modular than natural numbers. So we are going to introduce what I call floating universes. And basically the idea is just like instead of having a fixed natural number, you have a name that lives in some kind of global state. And you have a way to add constraints between your names, and they must form some kind of a directed acyclic graph to ensure that you can actually linearize it to natural numbers if ever you need to do that to ensure consistency. Okay, so that's a very well-known technique. It's very easy to implement in the kernel, which is probably the reason it was done at the time these things were introduced. It's a very old thing. Like I think it was introduced in 1987, so before I was born, our kernel. Okay, so how does it work? Yes, really, everything, most of the thing is done outside of the kernel. You generate fresh names outside of the kernel. You have a constraint that are added outside of the kernel, and then you just send the graph to the kernel, and it says yes, it's acyclic, or no, it's not acyclic, and then you did something wrong. So it's a very easy thing to implement, and it's solved because now you don't have to care about universes. You know, just have these free variables everywhere. Okay, yes, they do it differently, these people. Okay, so the reality is that it's not true. Why? Because basically, it's extremely wasteful as an implementation. In most of the developments, like what happens in practice is like you generate a literal bazillion universe levels, like pick any number of powers of 10, right? And most of them are just going to be, like, for unification purposes, they are completely useless in practice. They disappear. They are unified immediately by tactics. So you've got this huge graph, which is full of crap, right? So you send a huge graph of stuff that is actually not used, and you send that to the kernel, and it takes a lot of time, so that's very bad. And in practice, so fact, pick your favorite development, okay? Look at what it does if you collapse all the non-strict rules. Empirically, you have 3 universes. Okay? So very bad. So yes, you should be able to do everything. So it's all a fiction. In practice, you only want to have 3 universes, but since you don't know exactly when you create them, you don't know exactly at which level they will live. Like you can't use the free level thing with the numerals. But in practice, you could collapse them. So that's very bad for efficiency. That's like, yeah, people have been complaining about this for the kernel in a lot, a real lot. And the worst part is that, like, even if you're not aware, because like every time you write something, every time you write type in Kaggle, even when you don't write type because you just write a, you know, for all a, comma, then there is a type level that is generated, so you're going to pay for it in the end. And it's even worse when you use tactics, because tactics, under the hood, they generate a lot of universes and universe conversion problems. So everybody's paying for that, when in practice, you know that you could only use 3 universes. And it's even worse than that, because like this phenomenon of universe generation is extremely problematic. So I was mentioning that this morning to people that do unaware people, that actually, due to this design, that you've been lied to. Know it. The Coq proof assistant is a effectful programming language. There is one effect, which is this universe level graph thing going on. So in particular, you cannot evaluate things in parallel in Coq. You have to be careful about the order of evaluation because it might change the actual value of your terms depending on the way the universes are unified. So this is really horrible. The second point is that if you ever had a universe constraint issue, I hope for you that it's not the case. Like you still live in the paradise of not having to debug that, because like you get like a graph that is like several, maybe millions, there are several millions of universes with a constraint, and you're like, yes, there is a cycle somewhere. To introduce a cycle, you know, a cycle is a very global thing. So, okay, so yeah, floating universes seem like a nice solution, like it's easy to implement, but in practice, it's very annoying. Okay, so yeah, there's a famous horror story that you could not load Metacoq and QuickCheck together because there was a universe issue. I don't know whether it has been solved, but like, yeah, it's anyway. There is worse than that. Okay, now we are answering things that should not be told. Like really, if you exit this room, you should forget about this and keep that in the back of your mind, but not spread this knowledge. This is forbidden knowledge. Okay, so what is the type of type I? How you say? Well, it should be type J for some J smaller than I, or bigger than I, because that's kind of the rule. But I said that we do not generate levels from the kernel for a deep reason. So we somehow we want to have like it's called the what does it mean? Not primary, what's the name? Principality of the type. So we want to attribute a single type to that expression. and not something that comes from nowhere. So we need to have a notion called algebraic universes, so being able to write algebraic expressions inside our levels in the kernel to be able to type this type I. So we actually say that type I is type I plus 1, but due to the way the levels work in the kernel, this is not a term. But this is a type. This is not a term because terms cannot have algebraic levels because the way of the universe level algorithm work. So there is some kind of adjunction going on where you say, if I take a j that is strictly above I, and there is no other constraint, morally I'm talking about I plus 1. But this is not the same thing as I plus 1 because I plus 1 is not a term, it's a type. So terms and types are not the same thing in Quark. You've been lied to again. I'm sorry. So there is this is once again the Arduino principle striking in. And this is like really, this is like a forbidden law. Nobody knows about that. Now you know. It's like the ring, you're gonna die. You have 5 days before some ghost come through the TV screen to come at you. Okay, sorry. So this is another hot topic of the current work. Mathieu Souzeau, for instance, another Quark developer, is trying to implement an algebraic universe system that works with algebraic expressions, but it unearths a lot of Arduino smelling thing in the middle of the Quark kernel. It also resonates with other projects like the Multiverse project. So this is yet another kind of questions that have been ignored because it was easier to ignore them. But now that the time has come, it's time to clean up a bit what we've been doing. Right, and third and last point I wanted to discuss about the horrors of the Quark kernel is the guard. Okay, so brace again, because that one is great. So in CIC, you must ensure, for logical reason, that functions terminate. That is, you cannot write arbitrary fixed points, because otherwise you would get an inconsistent theory. You can, for instance, if you can write, for instance, natural numbers that satisfies this equation, then you lost. So as a strong constraint, every time you write a fixed point, it must be terminating. All functions must be total. So typically, if you look at paper presentations, people cheat and they say, oh, yes, I'm going to use what is called a recursor. So a recursor is just like a special kind of fixed point that is by construction terminating. So for instance, for natural numbers, it says, oh, if I have something at 0 and if for successor, if I assume something at n, I can prove it for successor of n, then I can prove it for any natural number, and you have the expected rule here. So this is really like a specific kind of fixed point. These ones are nice. And if you listen to the category people, they'll tell you, this is the natural number type. It has a universal property. So this is universal for your functions. Also good. Okay. This is not true. Because it's only true if you have extensional reasoning. You can't prove, yes, I mean, it depends how you phrase the things, but you have to be very careful about what you mean by your universal property, but in practice, it's very annoying. It doesn't work as expected. And it's worse than that if you really care about programming, because in programming, this is basically, assuming extensionality is basically conflating exponential algorithm with constant time. The functions that have the same input-output relation are the same. But this is not true. We all know as computer scientists that this is not true. You care about the complexity class of your functions. So this kind of, the ability to precisely capture the intentional behavior is critical when you program. We're not writing commutative diagrams, they're writing programs. And in particular, if you look at call-by-value evaluation, recursors are terrible. You have to box everything, otherwise you get to compute the branches. Like if you do an if-then else, for instance, you're not expecting that the branches are going to be computed inside an if-then else. But if you use a recursor, that's what's going to happen. So this is very bad if you do it that way. If you care about conversion, it's even worse than that. Universal, but universal property doesn't make sense. The question is open, what it means, and however you do it, it's not clear that you can encode all functions well-defined in natural numbers intentionally through recursor. So there is something extremely fishy here. what the category theorists have been talking about, only works in a world that is not really the world of programming. It's a world of extensional functions, which is approximation. Okay, so there is an extremely good news, which is that recursors, we said that the recursors are not good because they are not good enough for our purposes. So they are not fundamental in Coq, right? So that should be great. Instead, we have like this system based on fixed point and pattern matching. So you can implement the recursor just as some kind of fixed point that does the pattern matching. So that you don't have to read that. That's just the expected definition function. And the reason for this design choice is basically extraction. So people designed the inductive flag system to look like the OCaml programming language, so that it would be easy to transform a Coq proof into an actual OCaml program. And it's very important for efficiency in code-level the setting that you can write a program that really looks like what's going to be extracted. In particular, you can write things that are not intentionally recursor encodable. You can write, this is a typical example, like the function even. If you try to implement, so it's very easy to define, but if you try to implement it with recursors, then you're going to get something that doesn't compute exactly the same way. And it's very annoying. So you can try and going to exercise. I mean, you can encode it twice, but it's not going to compute the same. There is another bad news. Okay, so I said good news, they are not fundamental. Bad news, they are not fundamental. Why? Because since we have fixed point and pattern matching, that means that since arbitrary fixed points are inconsistent in general, we have to do something to ensure that we are consistent. So there is a mechanism that restricts the fixed points you can write in Coq to the good fixed points that do not threaten the consistency of the system. And this is called the guard. So this is a famous French, running a bit out of time. That's a famous French scene where, like the French, that was during the Napoleonic Wars. This guy was asked to surrender by that's a Brit here, and the guy says "merde," right? So what does the guard is supposed to enforce? So we care about the fact that the theory is consistent. So in particular, the function must be total, right? So there is a little bit of work by the Metacoq people. So there is a lot of closure conditions that you should assume about the guard. It's a bit weird, like you realize that things that you would have been naturally expecting from a guard, the guard criterion, are actually not required. So this starts to be a bit funny because like people designing a kernel did not think that way. Well, but in any case, it doesn't matter because like the idea is like you've got this, there are the bad fixed points and the good fixed points, and the more good fixed points you have, the better, right? Like you want to be able to write more programs, remember, as long as you're consistent somehow. So yes, so this is a vast understatement, I think. Maybe if you forget about modules. But yes, so there is this kind of miracle in the kernel that says whether a fixed point is actually terminating or not. So we don't even know the specification, right? It's been designed across the ages because people said, oh, I want to write this fixed point, and the guard says, no, could you please fix the guard condition so that the fixed point goes through? Like that. So yes, then. And clearly, this is in the kernel, and this is extremely critical. As I said before, if you have arbitrary fixed points, you're dead. Right? And just in the little bit of time that I have, I would like to give you like some foretaste about the kernel of guard condition. Okay, so first, what does total mean? Okay, we're saying you want your functions to be total. Okay. Let me give you an example. So CIC has what is called a call by name equational theory, right? So the only thing that is really important in CIC is weak head reduction. So please have a look at this function. So this is a fixed point, right? Loop that takes a dummy argument unit, and that returns units, but uses a dummy recursive call to something that's never going to terminate. So it's a loop that has a subterm that loops, but the subterm is not used by the function. So in call by name, there is no problem, right? Because like this let binding is not just going to disappear. It's not used. So it's not even inconsistent. This is just a constant function that returns unit. But in call by value, this is going to loop because it's going to first evaluate this and start looping. And the thing that should start to frighten you is that this fixed point here used to be accepted by the kernel, right? even though it's not total as per call by value, but it's total as per call by name. So in particular, there were funny examples where extraction would go completely awry due to these kind of situations. So it's not clear. So it is now forbidden, but it's not clear why it should be forbidden. Like, what does total mean? Again, is a good question. Point one. Point two. Okay, what is the worst you could figure that could happen if you have a guard that is not doing what you're expecting a guard to do? So you're like, oh yes, you know, you could be inconsistent, you know, like you get, if you allow more guard, like if the guard is more lenient, there's like you can reach falsity. That's bad. We don't want it. But apart from that, the only thing you can get is more functions. Seems legit, right? Like you have more function you can write. Okay, so there was this very funny example where a few years ago we realized that the guard condition was able to negate the following property. So that's propositional extensionality. It says that if you take two propositions P and Q, if P is equivalent to Q logically, then they are equal. Okay, and both in the homotopy theory and the set theoretic models, this should be true, right? So how come the guard condition, which is supposed to say when a fixed point is well defined, like what's the link between those two things? You know, like what the hell? Why the guard? There is no link whatsoever between this statement here and that thing here. And since we want to be compatible with both hot and sets, then there is like this is wrong. Like the guard condition should not allow to prove the negation of that thing. So that's very weird. Okay, so there is some kind of explanation of why this is wrong if you follow the hot thing, but like actually the reality is a bit more murky. So consistency is not enough. Like not proving false is a good thing. Like that's something you want, but you want more than that. And you want the guard condition to be as neutral as possible with respect to the possible world in which you will do mathematics. So the two most antagonistic ones we know as of today are homotopy type theory and the set theoretical model. So this is like classical mathematicians, and that's like the crazy people doing homotopy type theory. But maybe there are more models here we care about and we don't know about yet, because like these people did not exist like 30 years ago. So you know, like, and why the guard condition should what has the guard condition to do with that? Like, the foundation has nothing to do with the fact that function terminates or not somehow. But at the same time, yes, so you want the guard condition to allow as many functions as possible because you like writing a function in a natural way. There is even like a current of people who are critically relying on that. I'm not going to give names here, but they will recognize themselves. And clearly, whatever I'm saying here, this is not formal. Like we don't have any idea about what it means to be compatible with whatever mathematical model people care about. That's not a specification, I'm sorry. So we are in trouble. So the only model really understand is the recursive-based one, so there's small print here, and that's so there is a thing called nested inductive types, and if you hear the word, yes, you should start running. You don't even question what I'm saying, like you run. If you hear nested, you turn away and you run now. Anyway, so yes, we are supposed to understand that thing, right? So normally you should be able to understand the guard condition by combining recursives. And in an ideal world, you could say, yes, this is just elaboration. The kernel only understands recursives, and then the guard is some kind of a very simple thing. This is what the equation does. We have got people doing, so the lean people are kind of doing that. But as we said, like there are fixed points that are not exactly recursive. So depending on what you mean encodable, you might not be able to encode them in the way you expect it to be. In particular, an intentional notion of encodable. So there is a funny case where there are models that are inconsistent with the guard condition as it is implemented today. I can give you an example if you want to apply, like actual models, funny models. Yes, in particular, effects are really badly playing what we do in the guard. What does it mean to be encodable? Many questions. We've got a PhD student who started working on that. And this is really a hairy question. Like there are a lot of things, like most of the questions come from the fact that things are not very well defined. So we are really in the murky areas of terrible mathematics where we're discussing things that have the same name that don't on the same thing. Okay, so this is the kind of the conclusion of this section, which is like, who shall guard? Not me, I hope. let's conclude right in time. So theoreticians, they have strong beliefs about like the easiness of life. But in reality, there is such a thing as a wall with a lot of asperity. And when you try to implement a proof assistance, then actually you realize that reality matters. And then you cannot just say, yes, this is a very simple thing known for life, for ages in mathematics or whatever. Worse than that, like there is a mix between what we call diachronical and interindividual dialectics. So depending on the time of the day, you want something, but then after you want something else. So it's as the same person, so it's a bit annoying. And there are monsters everywhere. Like if you just like you lift a stone in the kernel, and then you realize that there are things that you just put it back immediately because you pretend not to have seen it, and you're like, yeah, we know it, no problem. It's there, it's somewhere in the stone. Don't lift it too much. But that is the Andrea's principle. We like it. That gives you, that gives me a lot of work. So I'm not going to be unemployed soon. People are still using proof assistance, and even though they are somehow not perfect because they are concrete and like actual objects that are implemented, you should not really fear this reality check. Like this is part of, I would say, engineering in a noble term. This is the real. The reality is complex. So yes, we have a lot of interesting things to work on. Still, time theory is not dead. It's as lively as ever, and I hope that you can also partake in this kind of work if you want to. So yes, do not be afraid and join us. And I think that's it. Thank you very much.